Welcome viewers. Have you ever touched a bulb immediately after switching it off? A few of you may have done it and may have experienced that its temperature is very high. Is it only the temperature which increases on passing current? Actually not. Its resistance also increases multiple times because the resistivity of a material is found to depend on the temperature. Different materials do not exhibit the same dependence on temperature. The resistivity of a metallic conductor is approximately given by rho T equals rho naught bracket 1 plus alpha T minus T naught, where rho T is the resistivity at a temperature T and rho naught is the same at a reference temperature T naught. Alpha is called as the temperature coefficient of resistivity. The dimensions of alpha is temperature raised to power minus 1. Now we shall discuss the variation of resistivity of a good conductor. Example is copper. Here you can see a curve being plotted between resistivity and temperature. The temperature is taken in Kelvin and note down the unit of resistivity, it is ohm meter. For the first 50-degree change of temperature, the corresponding change in resistivity is less, but if you observe the next 50-degree change, the change in resistivity is higher. So we can see that the resistivity of copper not only changes, but changes with different rates. Now the second variation is variation of resistivity of an alloy, and example is nichrome. Here you see a curve between resistivity and temperature again. This time for a change the curve is a straight line. So we can see that the variation of resistivity with respect to temperature is uniform and moreover it is very small. Resistivity of nichrome changes very little and that too at a constant rate. Now we shall study variation of resistivity of a semiconductor. This time for a change the resistivity is not increasing with temperature, rather it is decreasing with the rise in temperature. Resistivity of a semiconductor decreases with increasing temperature. Variation of resistivity with temperature can be understood with this equation: rho equals 1 upon sigma, which equals m upon Ne square tau. Let us understand the meaning of the symbols. Rho stands for resistivity, sigma is for conductivity, m is the mass of electron, n is the number density or number of charge carriers per unit volume, small e is for the charge on an electron, and tau represents relaxation time. Thus the resistivity of materials depends inversely on n number of charge carriers per unit volume, tau relaxation time. When we increase the temperature, the average speed of electrons increases. Thus the relaxation time tau decreases. In metals, n is almost independent of temperature, but the decrease in the value of tau with the rise in temperature causes rho to increase, as we have observed. Whereas in insulators and semiconductors, n increases with temperature. This increase more than compensates any decrease in tau. So that for such materials rho decreases with temperature. Alright, we all are very well aware that copper is a better conductor than aluminum, but still overhead power cables are almost exclusively made of aluminum. What is the reason behind this? Let us find an answer to this. To do this, we will solve one question. Two wires of equal length, one of aluminum and the other of copper, have same resistance. Which of the two wires is lighter? And explain why aluminum wires are preferred for overhead power cables. Let us solve this problem. It is given that the length of both the wires is the same. We have taken it to be L. Resistance are also given to be the same. and we have to compare their masses. So how do we compare their masses? We know that mass equals volume into density. So for first metal, that is for aluminium, mass becomes volume of aluminium into density of aluminium. Similarly, for the second metal, we have mass M2, which equals volume of second metal into density of second metal. So to compare their masses, we divide these two equations and we get M1 by M2 equals V1 into D1 upon V2 into D2. Alright, we know that volume equals area multiplied by length. So using that in both the equations, since both the lengths were the same, so these L1 and L2 are going to be cancelled out and we are left with M1 upon M2 equals A1 D1 upon A2 D2. Densities are already given in the question, but we are not aware of the ratio of their areas. So what we can do for this, we will be using this condition that the resistance of both the materials are the same. So let us number it as equation 1 and try to find out the ratio A1 by A2 by using this condition. So this condition says that both the resistances are the same, R1 equals R2. We also know that resistance equals rho L by A, and similarly here it is rho L by A. For first material, let the resistivity is rho 1, for the second it is rho 2. Also L1 and L2 are again the same, so these two get cancelled out, and from this expression we get the value of A1 by A2, which was required in equation 1. So solving this, we can easily see that rho 1 by rho 2 equals A1 by A2. Now the value of A1 by A2 can be replaced in this equation, and then we will have M1 by M2 equals rho 1 by rho 2 into D1 by D2. Now all these four parameters are given in the question. If you put the value, then you will be getting that M1 by M2 comes out to be 0.46. So aluminum is lighter than even half of copper's mass. Consider a conductor with endpoints A and B. And let this conductor carries a current I from the point A to B. The potentials of A and B are VA and VB respectively. Since the current is flowing from A to B, so obviously B is at a lower potential and A is at a higher potential. So if we calculate the potential difference VB minus VA, then it will be a negative quantity. Let us imagine a time interval T in which charge is flowing from A to B. So in time interval T, if the current is I, then the charge flowing will be I into T. That is, in time T, this much is the charge which flows from A to B. Now this charge Q, when it was A, had a certain potential energy. Let that potential energy is UA. From the definition of potential energy, we know that this potential energy will be Q into VA, whereas the potential energy of the same charge when it reaches B becomes UB, which is Q into VB. From these two expressions, we can find the change in potential energy of the charge when it moves. So that change in potential energy can be given by the final potential energy minus initial potential energy, which comes out to be Q Vb minus Va. Now, as we have already understood from equation, let us number this as equation 1. From equation 1, Vb minus Va is a negative number. So, putting its value as minus V, we get the change in potential energy as minus Q V. Also, Q equals IT. So, delta U becomes minus IT into V. Okay. If the potential energy is decreasing, then from conservation of energy, we can say that the kinetic energy must be increasing by the same amount. While saying that, we have considered that there is no loss of energy. So, in that case, the change in kinetic energy should be this much, that is IT into V. But if the kinetic energy of the electrons increases, it means the electrons will be speeding up. But does it happen? Actually, no, since the motion of the electrons is not uninterrupted. They keep on colliding with the ions located in their path and the atoms located in their path while moving through the conductor. In that process, they tend to lose their kinetic energy and actually they never accelerate. So, all this kinetic energy is ultimately converted into heat energy in those collisions. So, we can say that this kinetic energy ultimately appears as the heat energy, and W becomes ITV. Here W is the heat energy which is evolved in time interval T. So, this much is the energy which is lost when electrons move through the conductor. Now, let us introduce the concept of power. As we know that power is the energy lost per unit time. So, let us do that by proceeding with this equation. Power equals energy per unit time or the work done per unit time. With that, we get VIT divided by T. So, one expression for power is VI. Using Ohm's law, it can also be written as I square R, and it can be written as V square upon R also. So, these three are the different expressions for power. The expression for power is that power equals I square R. It suggests that power obviously depends upon current and resistance. Okay. From this expression, we can understand that why the transmission cables carry power at a very high voltage. It is the power loss or ohmic loss in conductor of resistance R carrying a current I. It is this power which heats up, for example, the coil of an electric bulb to incandescence, radiating out heat and light. So, we have understood that what heats up current carrying wires. Now, the question is, where does this power come from? We need an external source to keep a steady current through the conductor. It is clearly this source which must supply this power. In simple circuit shown with a cell, it is the chemical energy of the cell which supplies this power for as long as it can. The expression for power shows the dependence of the power dissipated in a resistor R on the current through it and the voltage across it. The expressions for power show the dependence of the power dissipated in a resistor R on the current through it and the voltage across it. One of those expressions for power is P equals I square R. We will use this expression to explain that why do the transmission cables from the power station to the domestic or to the industrial supplies carry voltages at very high values. So, let us suppose that this is the transmission cable from power station to domestic or industrial supply. It has a finite resistance, say RC, and it is carrying a current I. As we are aware that these transmission cables carry a certain power, it may be in megawatt or maybe kilowatt or maybe any other unit. So, let us suppose that this cable has to carry a power P. Using this, we can find out the power dissipation in this cable. As this expression suggests, the power dissipated in the cable is PC equals I square RC. We can find out the value of I from this information. Power is P, current is I, and let the voltage carried by this wire is V. Then from here we know that power equals VI, so I becomes P upon V. If we put this value of current in this expression, then power dissipated in the cable becomes P square upon V square into RC. Now, if we look at this expression, power to be carried by the cable is constant, we can't help it. What about RC? It is the resistance of the transmission cable. Again, we almost can't help it. What we can do to reduce power? We can keep the voltage at a higher value. So, this is why the transmission cables carry voltages at very high value to ensure the less power loss during transmission. The power wasted in the connecting wires is inversely proportional to V square. The transmission cables from the power station are hundreds of miles long and their resistance RC is considerable. To reduce PC, these wires carry current at enormous values of V, and this is the reason for the high voltage danger signs on transmission lines, a common sight as we move away from the populated areas. Using electricity at such voltages is not safe, and hence at the other end a device called a transformer lowers the voltage to a value suitable for use. You will learn about transformer in later chapters. You may find it very interesting to see the power ratings of the appliances used in your homes, be it your TV, AC, geyser, washing machine or something else. In festive seasons, especially on Diwali and Christmas, many of us have enjoyed decorating our houses with colorful lights. Here is a picture of one such decorative light. But those who have used this light must have also struggled with the problem of all or many of the bulbs not glowing at all. It is because of the fact that these bulbs are connected in series, and if one of the bulb or LED blows off, then none of the bulbs will operate. On the other hand, the lights and appliances connected in our homes do not behave like that. They operate independently. The reason behind this is that in houses all the devices are connected in parallel. So, now the topic of discussion is series and parallel combination of resistors. Two resistors are said to be in series if only one of their endpoints join and they carry equal current. If a third resistor is joined with the series combination of the two, then all the three are said to be in series. Clearly, we can extend this definition to series combination of any number of resistors. Two or more resistors are said to be in parallel if one end of all the resistors is joined together and similarly the other ends joined together. Consider two resistors R1 and R2 in series. The charge which leaves R1 must be entering R2. Since the current is measured as the rate of flow of charge, so both the conductors will be carrying the same charge and hence the same current. Let us name the first resistor as R1, the second as R2. Let these points are A, B and C. Now the voltage drop across the first resistor between the points A, B is I into R1, where I is the common current which is flowing through both the resistors. The voltage drop across the second resistor can again be given by Ohm's law, and it is I R2. If we calculate the total potential difference between the two ends A and C, V1 plus V2, so it becomes I R1 plus I R2. Taking I as common, we are left with V equals I times R1 plus R2. If we consider an equivalent resistance which has been subjected to the same voltage and same current, then the equation for that resistor will be written as V equals I into R equivalent. Comparing these two equations, we can see that R equivalent equals R1 plus R2. So this is the formula for the series combination of two resistors. If resistors are connected in series, then the individual resistors are added linearly to give the resultant resistance. We can generalize this formula for higher number of resistors also. For example, for 3 resistors, it will become R1 plus R2 plus R3. If we add another resistor R3 here, so the formula will become R equivalent equals R1 plus R2 plus R3. Similarly, it can be generalized for any number n of resistors and can be written as R1 plus R2 plus R3 up to Rn. Similarly, if we consider the parallel combination of two resistors, these are the two resistors and we have named them as R1 and R2. Any current which has approached this point will be divided into two parts, since charge cannot be destroyed. So now we can write that I is equal to I1 plus I2, of course. Since both the resistors are connected between the same points, so the voltage across them is obviously the same. Let the common voltage is V. Then for the first resistor, we can write V equals I1 R1, giving the value of I1 as V1 by R1, and for second resistor we have V equals I2 R2, giving I2 equals V by R2. If we place the values of I1 and I2 from here in this expression, then we will get I equals V by R1 plus V by R2. So putting the values of I1 and I2 from these equations in this equation, we get I equals V by R1 plus V by R2. Taking V as common, we have this expression. If the combination was replaced by an equivalent resistance R equivalent, we would have by Ohm's law I equal to V upon R equivalent. So by comparing these two equations, we can easily see that here in place of 1 upon R equivalent, we can see 1 upon R1 plus 1 upon R2. So on comparison, 1 upon R equivalent becomes 1 upon R1 plus 1 upon R2. This is the formula for the parallel combination of two resistors. Again, it can be generalized for any number of resistors. Say if the resistors are 3, then it can be written as 1 upon R equivalent equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3, and it can be generalized to n number of resistors as well. So after learning about these combinations, to test your understanding and to strengthen your concept, you may solve a few problems from NCERT exemplar problems. While learning about current electricity, it is impossible to not to discuss the device which makes the current to flow continuously. The name of this device is an electrolytic cell. The image of the cell shows the shape in which we use it, be it in AAA cell for our remote controls or in AA cell for the wall clocks. The second image shows the form in which it is available in the laboratory. So our topic of discussion in this class is a cell and its parameters. We have already mentioned that a simple device to maintain a steady current in an electric circuit is electrolytic cell. We have already mentioned that a simple device to maintain steady current in an electric circuit is the electrolytic cell. Basically, a cell has two electrodes called the positive P and the negative N. They are immersed in an electrolytic solution. Dipped in the solution are the electrodes, and the electrodes exchange charges with the electrolyte. The positive electrode has a potential difference of V plus between any of its part and a point immediately close to it inside the electrolyte. Let this potential is represented by V plus. This is the potential of the positive terminal. Similarly, the negative terminal has a negative potential at a point very next to it lying inside the electrolyte. This potential of the negative terminal is represented by V minus, and this is obviously a negative potential difference. The difference of the two potential difference, the difference of the two potentials is Vp minus Vn, which becomes V plus minus minus V minus, and it becomes V plus plus V minus. This potential difference between the two electrodes is termed as the electromotive force of the cell, and it is denoted by E. Thus V plus V minus is greater than 0. Note that E is actually a potential difference and not a force. The name EMF, however, is used because of the historical reasons and was given at a time when the phenomenon was not understood properly. The electrolyte through which a current flows has a finite resistance R called as internal resistance. Consider the situation when cell is connected across a resistor R. In this situation, the relation between the potential difference and this EMF is given by V equals E minus IR, where I is the current drawn from the cell. In practical calculations, internal resistance small r of the cells in the circuit may be neglected. The actual values of the internal resistances of cell may vary from cell to cell. We also observe that since capital V is the potential difference across R, so by Ohm's law, V can be written as I into R. From this expression, we can get the value of the net current. And this comes out to be E upon capital R plus a small r. However, in order to get the maximum current from this cell, the external resistance capital R should be 0. So, in that case, the maximum current will be E upon small r. But practically we never do that, since such a high value of current may damage the cell. Let us solve a numerical problem based on this. A battery of EMF 10 volt and internal resistance 3 ohm is connected to a resistor. If the current in the circuit is 0.5 ampere, what is the resistance of the resistor? What is the terminal voltage of the battery when the circuit is closed? So, let us solve this problem now. I have drawn the corresponding diagram. Here is a cell, rather a battery of 10 volt with an internal resistance 3 ohm, an external resistance, unknown resistance R is connected, and the current in the circuit is 0.5 ampere. We have to calculate the resistance R and we have to calculate the terminal potential difference. So, from the formula of current, we can write I will be equal to E upon capital R plus small r. E is the net voltage and capital R plus small r is the net resistance. Putting the values of all the terms, we can easily find out capital R. I is 0.5, E is 10 volt, capital R we have to find out, and small r is 3 ohm. By cross multiplying it, we can reach this expression, and by taking 0.5 on the other side, it becomes 8.5, and which gives the value of R as 17 ohm. So, the resistance R is 17 ohm. The second part, we have to calculate the terminal potential difference, and as we know, the relationship is V equals E minus IR. So, we have to calculate V. E is 10, I is given 0.5 and R is given to be 3 ohm. So, we have 10 minus 1.5 equal to 8.5 volt. Now, some work to do for the viewers. On solving, we get R equal to 17 ohm and terminal potential difference equal to 8.5 volt. Now, we have some work to do for the viewers. We are using cells or batteries in a lot of ways, in remote controls, in laptops, in mobile phones, in toy cars, and even e-rickshaws. Are they all same? If not, then what are the difference in them? So, I leave you with this question. Thank you.